Let us discuss about the oxidation and reduction of aldehyde and ketones. So first we'll discuss about the oxidation of aldehydes and ketones. So we have number of and the variety of oxidizing agents available to oxidize aldehyde and ketones. Now aldehydes being less crowded and also due to the presence of one hydrogen at the carbonyl carbon are more easily oxidizable than ketones. So ketones are more difficult to oxidize. Now the first oxidation is with a hot alkaline KMnO4. This is a very strong oxidizing agent. We can also use hot and concentrated nitric acid also. So any strong oxidizing agent can be used. Any strong oxidizing agent. So OA stands for oxidizing agent. Now if you are using aldehyde, now look at the aldehyde group only. So aldehyde group can be oxidized with any strong oxidizing agent to carboxylic acid. So it gives the acid with the same number of carbon. Acid with the same number of carbon atoms. So if the number of carbon atoms remains same, it means your parent compound is an aldehyde. For example, CH3, CH3, CHO on oxidation gives a carboxylic acid with the same number of carbon atoms. So if the number of carbon atoms remains same, it means the parent compound is an aldehyde. Now ketones on the other side are more resistant to oxidation, and ketones on oxidation results in the formation of an acid with a less number of carbon atoms. It may be one carbon less, maybe two carbons less, but that is not important. Important is whether the carbon remains same or it's less number of carbons. If the number of carbons remain same, it means it's an aldehyde. If there is a loss of carbon atoms, it means the parent compound was ketone. Now in this case, when we oxidize, then two possibilities are there, either to break this bond A or to bond B. Now if we are breaking bond A, then the acid obtained is this. If we are breaking bond A, and if we are breaking bond B, then the product obtained is this. So it gives a mixture of acids, but each acid contains a lesser number of carbons than the parent ketone. So ketones on vigorous oxidation gives, or strong oxidation gives, a mixture of acids each containing a lesser number of carbons than the parent ketone. For example, if we oxidize acetone, this on vigorous oxidation gives an acetic acid with one carbon less, and the one carbon is lost in the form of a carbon dioxide gas and water. So there is a loss of one carbon, and this is a major product called acetic acid. On the other hand, if you are oxidizing the propanol, which is an isomer of propanone, it gives an acid with the same number of carbon. That is called propanoic acid. So in this case, the number of carbons remains same. The next is the oxidation with the Tollen's reagent. Oxidation with the Tollen's reagent. Now, Tollen's reagent is ammoniacal silver nitrate. Ammoniacal silver nitrate. And Tollen's reagent has a formula, it's a complex AgNH3 whole twice and OH. And Tollen's reagent only oxidizes aldehydes, but all aldehydes, whether it's aromatic, aliphatic, oxidize aldehydes to acids and itself reduced to form a silver mirror. And the formation of the silver mirror is used to distinguish aldehyde from ketones. So Tollen's reagent is used to distinguish aldehyde and ketones. So whenever you have to write a test, you prefer Tollen's reagent test. Now this is the equation involved. This is aldehyde group, and on oxidation with Tollen's reagent, AgNH3 whole twice and OH, it gives a salt which can be acidified to give the final acid, and it gives a silver mirror. And the side products are ammonia, water, like this. So we can distinguish this propanol and propanone by using a Tollen's reagent test. So you prefer the answer in this tabular form. So write the name of the test. It's a Tollen's reagent test. Write the formula of the reagent used, AgNH3 whole twice, OH and warm. You write the observation, it gives a silver mirror, and it gives a negative test, so you can write negative test. But for the positive test, you have to write the observation that propanol gives a silver mirror. The next is oxidation with a Fehling solution. Now, Fehling solution is a mixture of Fehling A, which is a copper sulfate solution, blue color, and Fehling B is a sodium, potassium, tartrate, which is also known as the Rochelle salt. And Fehling solution only oxidizes only aliphatic aldehydes. Only aliphatic aldehydes. It does not oxidize benzaldehyde. Now this is the equation involved, RCHO. This is cupric ion from the copper sulfate. This is a hydroxide ion and warm, and it gets oxidized to a salt, and the Fehling solution itself reduced to form a reddish brown precipitate of cuprous oxide. And formation of this indicates the presence of an aldehyde group. So this is oxidation with Fehling solution, and in this case the oxidation state of copper changes from +2 to +1. So whenever you have a question to distinguish between aldehyde and ketones, you prefer either Tollen's or Fehling. Now next is a reduction of aldehyde and ketones. Aldehydes and ketones. Now aldehyde and ketones can be reduced to alcohol. The first is reduction to alcohols. So aldehyde on reduction with a lithium aluminium hydride or with sodium borohydride gives a primary alcohol. This we have already done, primary alcohol. And ketones, again look at the group only. Under similar conditions using lithium aluminum hydride or sodium borohydride gives a 2-degree alcohol. Gives a 2-degree alcohol. So there is no change in the number of carbon atoms, and if both are present, they both gets reduced to their respective alcohols. For example, this. Now this is the example given, and we are reducing it with the sodium borohydride. Now in this case, the aldehyde and ketone, they both are present, so they both reduce to form the alcohol. Now aldehyde forms 1-degree alcohol, while ketone is reduced to form a 2-degree alcohol. So this is the product obtained. So this is a reduction to alcohols. Now next is reduction to alkanes. So it's a complete loss of oxygen and gain of hydrogen. Reduction to alkanes. Now this is carbonyl group and can be reduced to this hydrocarbon alkane either using zinc amalgam. Amalgam means alloy of any metal with mercury in hydrochloric acid. Now this is called, so we are supplying 4 hydrogens. Now this is called Clemmensen's reduction. So all these name reactions are very specific. When we say it's Clemmensen's, it means you have to use only zinc amalgam in HCl. Again, there is no change in the number of carbon atoms. So CO group is reduced to CH2. But we can also reduce CO group to CH2 via hydrazone formation. So we are using hydrazine. It gives a hydrazone, and this hydrazone can be converted into this by using KOH glycol. This is hydrazone. Now this reduction of carbonyl group to alkane via hydrazone is known as a Wolff-Kishner reduction. Wolff-Kishner reduction. Now one example is this. This is a given benzene, and we are performing a Friedrich-Kraft acylation using propanol chloride in the presence of AlCl3. This is a Friedrich-Kraft acylation. It gives the aromatic ketone COCH2CH3, and this can be reduced to propyl benzene by using hydrazine followed by reaction with the KOH glycol. It gives a propyl benzene. So we have used Wolff-Kishner reduction, but you can also use Clemmensen's. So this is all about the oxidation and reduction of aldehydes and ketones.